Hey guys, so in the previous video, I talked about the notion of electric fields and electric flux a lot. And the reason I wanted to do that is a lot of the tools we use when we talk about magnetic fields also apply to electric fields. So if I were to tell you that magnetic fields are a vector field that exists, right away, there are some things you know about magnetic fields. One thing you could say is, I imagine a vector field. Remember, a vector field is an idea from math. I'm being arbitrary here. I imagine a vector field as a whole lot of arrows filling the volume of space. And at every location, there's an arrow with a magnitude and a direction. Basically, at every location, there's a vector. Well, if a magnetic field exists, that means that's probably going to be the mental image I have in my mind of the magnetic field. So I also could place a surface somewhere and ask how much arrows pass through that surface. So that means I could talk about the concept of magnetic flux. So the definition of magnetic flux is very similar to the definition of electric flux that we talked about in back in chapter 16. So magnetic fields are symbolized by the letter B, because if you turn a B on its side and remove the straight line, you have something that kind of looks like an M. So the magnetic flux through any surface is defined very similarly to the electric flux through any surface. You just, instead of the letter E, you have the letter B, and instead of electric field, you have magnetic field. But nothing really changed mathematically to what we're doing. So if I have a magnetic field that is filling space, I will choose my magnetic field to be nice and uniform because that is easy to work with. I could place a surface area in space. That surface area might be somehow aligned or oriented in a certain direction. I could say the flux passing through this surface is the strength of the magnetic field. Presumably that would be given somehow. The size of that surface, area A, so that'll be something measured in meters square, times the cosine of the angle between that surface area and the angle between the magnet and the magnetic field. So this is the exact same thing I talked about when I discussed electric flux, only instead of the letter E and an electric field, I have the letter B and a magnetic field. Mathematically, nothing I did changed. Now, before we said you could envision or you could have a mental image of your mind as positive and negative charges as locations where the electric field is created for the positive charge and locations where the electric field is destroyed for the negative charge. Now, that's not really physically what happens, but for the purpose of a mental image, a mental picture in our mind, we could think of it that way, because the electric field arrows always point away from positive. So I imagine the arrows are created and move away from the positive charge. And then the electric field arrows always point towards the negative charge. So I think of the negative charges gobbling them all up. Now, magnetic charges, unlike electric charges, magnetic charges do not exist. So this is going to have an interesting consequence. There's no such thing as a source or a sink in terms of magnetic field lines. And as a result of this, magnetic field lines have no beginning and no end. So if you think of arrows, kind of like in the previous slide over here, over there, if these arrows have no source or no sink, no location where the arrows are coming out of or going into, there are two possible geometries for a magnetic field. A magnetic field could be either in a closed loop, because the closed loop will have no beginning and no end, or a magnetic field could be infinitely long, because if you're infinitely long, you have no beginning and no end. You extend out to infinity. Now, if you think about it, you could convince yourself that as a result of the magnetic field lines having no beginning and no end, any magnetic field that enters a closed surface must also exit that closed surface. So we're beginning to allude to a notion of Gauss's law for magnetic fields. So take any closed surface, and if you have a magnetic field line passing into that surface, you will have a magnetic field line exiting that surface as well. So Gauss's law for magnetic fields could be written in the simple form of the magnetic flux through a closed surface will always be zero. There's no such thing as a magnetic charge. Another way I could think of that is Q magnetic charge is always zero. So the flux through a closed surface is equal to the charge inside that surface. If the charge inside that surface is zero, well then there you go. So we have the notion that magnetic fields exist. We also have the notion that magnetic charges do not exist. So, okay, well, how could you create a field if there's no source or sink for that field to exist? Many luminaries of our time, many really intelligent people have asked the question, magnets, how do they work? So if you are a magnetism enthusiast, you could study this topic more in depth. And now this is an aside and me going on a rant, but the magnetic field is really just a certain manifestation of the electric field. And that comes about due to special relativity. Now, we're not really going to go deep down this rabbit hole within this course, but if you imagine, take a charged particle and throw it at somebody. Now, when you throw a charged particle at a person, you would see an electric field because, you have a charged particle, and you would see a magnetic field because magnetic fields are created by charged particles. However, you could imagine that, let's take a different perspective. Let's say while you throw that charged particle at somebody, your best friend is running along with that charged particle and watching. So your best friend's point of view as they're running next to the particle, they would not see the particle moving. From their perspective, from their reference frame, the particle appears stationary to them. So your best friend would only see an electric field. Now, physics should be consistent. The rules of physics, the rules by which nature works, should not depend on who is watching, should not depend on the reference frame. So if your friend sees an electric field only, and if you see a magnetic and an electric field, then you could reason that a magnetic field is probably just a certain manifestation of the electric field. In other words, a magnetic field is just an electric field that is observed by a certain observer. So in this case, you are an observer that is moving compared to the particle, or from your point of view, the particle is moving. But to really reconcile electric magnetic fields, you have to go into Lorentz transformations and special relativity. We're not going to really go down that rabbit hole. So on a fundamental level, a magnetic field is just a special manifestation of the electric field due to the fact that the charges that create the electric field are moving from your perspective. So, what is a magnetic field? Well, magnetic fields, as I said, they are created by moving charges. A charge at rest, like I said, will create an electric field, but that charge will not create a magnetic field. A charge that is moving will create a magnetic field. And an example of moving charge is electric current flowing through a wire. We've talked about this. And this was actually how, way back when in the 1800s, the study of electricity and the study of magnetism were separate disciplines of science. People had no reason to think that they were related. But then Ampere, named the guy with the electric current unit named after him, he was preparing to give a physics lecture, and he noticed that when a wire was turned on, there was a nearby compass, and that magnetic compass was affected by current flowing through the wire. And this was an accidental discovery, but this was very significant because this proved that the science of electricity and the science of magnetism are actually connected to each other. So current flowing through a wire is one example of how to create a magnetic field. Now, we said magnetic fields are created by moving charges. If we have a magnetic field, that is a vector field. So that is a quantity with a magnitude and a direction. And to fully specify a magnetic field, we need to specify both magnitude and direction. So how can I do that? Well, first I'll talk about the direction of a magnetic field. So to determine the direction of the magnetic field flowing through a wire, point your thumb in the direction of the wire. We'll assume the wire is really long and straight, so you have an infinitely long straight wire. Point your thumb in the direction of the wire. Make sure you're using your right hand. And notice that your forefingers curl in a certain direction around the wire. So your forefingers curl nicely in one direction and not so nicely in a different direction. So there is the direction of the wire. If I point my thumb upward along the direction of the current, notice that my fingers curl this way. My fingers do not curl that way. So if I am on this side of the wire, my fingers would be pointing towards me from my perspective with the computer screen in front of my face. If my fingers were on this side, they would be pointing into the computer screen based on the wire current in the wire flowing upward. So this is one version of the right-hand rule. There is another version of the right-hand rule that I'm going to talk about, and I'm going to stop the video here. In a future video, I'm going to have a picture of my wonderful face that you'll all get to see me manipulating my fingers and my arms for all this right-hand rule stuff.